Hi everyone, today we're doing 9.4 part 2, which is going to be about the geometric series and nth term test for divergence. First we're going to do the geometric series test because it's something we've already learned, so it should be a review. So it says that a geometric series in the form of the sum from n equals 0 to infinity of a times r to the n, or perhaps it starts with n equals 1 and it goes to infinity of a times r raised to the n minus 1, such that a cannot be equal to 0. The geometric series will diverge if the absolute value of r is greater than or equal to 1. Remember that this r, let me highlight it, because no matter the form, if it starts with 1 or if it starts with 0, that r is going to be equal to the common ratio. So when that common ratio is greater than or equal to 1, we know that those terms are going to get larger and larger, so the geometric series will diverge. If the absolute value of r is less than 1, then the series is going to converge, and that sum is going to be equal to the first term over 1 minus the common ratio. So this is a formula that you probably learned first back in Algebra 2. Let's take a look at some examples. So we're going to determine whether these series converge or diverge. So let's take a look at this first one. Sorry, I'm just trying to get this to be large and not crooked. All right, so we have the sum from n equals 1 to infinity of 3 over 2 raised to the n. So it might help you to notice that 3 is just a constant, and therefore my common ratio is 1/2 raised to the n, because if 1 raised to the n will just be 1. So here I can see that my common ratio is 1/2, and the absolute value of 1/2 is indeed less than 1. Therefore, the series will converge, and it's going to converge to the first term all over 1 minus that 1/2. Now the first term, I just need to be very careful. Since the series starts with n equals 1, I would plug in 1 to find the first term, and a sub 1 is going to be 3 over 2 to the first power, or 3/2. Some might look at it and think that the first term is 3, but since it starts with 1, that isn't exactly correct. So now when I clean this up, I'd get 3/2 over 1/2, and I'd find that the series converges to 3. All right, let's take a look at my next example. I have the sum from n equals 1 to infinity of 3/2 raised to the n. So here I notice that the 3/2 is my common ratio. And since the absolute value of 3/2 is greater than 1, that means that this series will diverge. And let's take a look at my next one. So here I'll have the sum from n equals 2 to infinity of 3 times negative 1/2 raised to the n. So here I can see my common ratio is negative 1/2, and the absolute value of 1/2 is indeed less than 1. Therefore, I know the series will converge. And it's going to converge to the first term all over 1 minus negative 1/2, since that common ratio is negative. In my first term, I notice I'm starting with n equals 2. So when I plug in a sub, so this is interesting. The first term, a sub 1, occurs when n equals 2, since I start with 2. So I have 3 times negative 1/2 raised to the second power. So I have 3 times 1/4, which is 3/4. So there's the first term of my series. And when I clean this up, I get 3/4 over 3/2. And so therefore 3/4 times 2/3. So you can see you're left with 1/2. So that is your review of geometric series with those 3 examples. And now we're finally going to get to the first new item on the agenda, which is the nth term test for divergence. This is the first thing that's truly new in section 9.4. So the nth term test is for divergence only. So that's important. It's the nth term test for divergence. And it says if the limit as n approaches infinity of a sub n is not equal to 0, then the series diverges. And if you think about it, that totally makes sense. If the terms of a sequence are increasing, it's impossible for the series to diverge. So that limit has to be equal to 0. Note, this does not say that the series will converge if the limit is equal to something else. So that limit could be equal to 0. That doesn't necessarily mean that it's going to converge. It means it might converge. But we do know if the limit is not equal to 0, it is definitely going to diverge. And let's go ahead and get going. It's important, I guess let's read through this. Here, it's just what I just said. But if the limit is equal to 0, this doesn't tell us anything. It's inconclusive. The test fails. And you must use another test. We're going to learn a lot of tests. But this is a great time saver, and it should always be the first, not the second, but the first test you use. And usually this could be a spot check. So you can just take a look at your sequence, and if you notice, hey, the limit as n approaches infinity is definitely not going to be equal to 0 here, you've saved yourself a lot of time. All right, so let's get into it. Still think that's a little crooked. All right. So I have the limit as n approaches 1 to infinity, the series from n equals 1 to infinity of 2n plus 3 over 3n minus 5. So I'm taking a look at this, and I'm noticing if I take the limit as n approaches infinity of your a sub n, so which is 2n plus 3 over 3n minus 5, I know that the limit here is 2/3 because I know that these powers will take over, and therefore I'll have a horizontal asymptote at 2/3. And this is not equal to 0. Therefore, the sum from n equals 1 to infinity of 2n plus 3 over 3n minus 5 will diverge. And now we have to start giving reasons by the nth term test. So it's important that you start naming the test that you're using. I have my work up here to prove that I use the nth term test. And I want to make a little note here. The series will diverge here. And we just proved that. However, the sequence a sub n equals 2n plus 3 over 3n minus 5, the sequence will converge to 2/3. That's what that limit is saying. The limit says that that sequence will converge to 2/3. Since that sequence is not converging to 0, I know that the series is going to diverge. So the distinction between the sequence and the series is really important. All right, let's look at B. I know I've got 4 examples here. We're going to go through A, B, C, and D. All right, so here I'm looking at the sum from n equals 1 to infinity of n factorial over 2 times n factorial plus 1. So let's take a look, and let's do the limit as n approaches infinity of n factorial over 2 times n factorial plus 1. So think about what's happening as n goes to infinity. You know that these n factorials right here are going to dominate both the numerator and the denominator, and that this plus 1 right here becomes pretty insignificant as n goes to infinity. So it's kind of like a horizontal asymptote in a way. We know that there's a 1 here in front of this n factorial. So as n goes to infinity, and that plus 1 that I highlighted in yellow becomes insignificant, I know that each term is going to approach 1/2, which is just going to be those coefficients of the n factorial. Therefore, the series will diverge by the nth term test. And that's example 2, or part B. Let's look at C. So now I'm looking at the sum from n equals 1 to infinity of 3 to the n minus 2 all over 3 to the n. So let's evaluate the limit as n approaches infinity of 3 to the n minus 2 all over 3 to the n. Hopefully you're looking at this and you're saying as n approaches infinity, that minus 2 becomes insignificant, and therefore it's going to follow the pattern of 3 to the n divided by 3 to the n, which will just give me a 1. Hopefully that's what your gut is telling you. What I want to do is I'm just going to take this opportunity to review L'Hopital's rule. So what I have here as n approaches infinity is I have a really big number over a really big number, because 3 raised to the n will get very big in both the numerator and the denominator. So I can use L'Hopital's rule, which says that this limit will be equal to the limit of its derivatives. So therefore, what's the derivative of 3 to the n minus 2? Well, the derivative of 3 to the n is 3 to the n times the natural log of 3, and then minus 0, all over 3 to the n times the natural log of 3. And here you see these cancel, and you are indeed left with just a 1. So since this is a 1, which is not equal to 0, I can say that the sum from n equals 1 to the infinity of 3 to the n minus 2 all over 3 to the n diverges by the nth term test. All right, down to our last one. Let's take a look. So here on part D, I would start out by taking the limit as n approaches infinity of 1 over 1.1 raised to the n and seeing if I get a 1 or a 0. Well, I get anything else other than a 0, really, if I'm using the nth term test. So here I notice that the denominator is getting really, really, really large. And if the denominator is getting really large as n goes to infinity, that means the ratio of 1 over those really big numbers gets smaller, and it indeed goes to 0. But remember, this means the series might converge. So it has failed the nth term test for divergence, but that does not mean that it definitely converges. It means it might converge. I need to use another test. And now as I'm looking at this, I see that what I should have done was notice that this is a geometric series. If I look at this again, should have looked more closely, I could rewrite this sequence as 1 over 1.1 raised to the n. And so I see this is geometric, and my common ratio is 1 divided by 1.1. And so if I'm looking at 1 over 1.1, I got to check and say, is 1 over 1.1 less than 1? And if it is, that means that it will converge. And since that's true, this will converge. So the series will indeed converge to the first term all over 1 minus 1.1. And no, 1 over, just kidding, 1 over 1.1. That would have been really bad. And now the first term, since I'm starting with n equals 2, a sub 1 is going to be 1 over 1.1 raised to the second power. So cleaning that up a little bit, if I have 1 over 1.1 squared, oh goodness, that gives me 100 over 121. When I take 1 minus 1 over 1.1, I get 1/11. And then when I clean that up, I get 100 over 11. So just a little bit of arithmetic there. That's going to be, if I plug that in my calculator, I get 9.09091. Okay, so to recap, what we learned today were 2 tests in this. The second term was the nth term test for divergence. Remember, divergence only. And before that, we reviewed the geometric series test.